Great. Hello, everyone. This is your host, Nalti. Hope you guys had a great weekend. Um, we are in the fifth week of our fellowship. Hope everyone's learning and hunting bugs in Summa Solvency's code base. If not, I highly recommend you sync with your team and start working as the deadline to submit your security reviews is fast approaching. And we also recommend the teams to take a look at the bounty on the security analysis of Suma's Merkle sum tree. We've also extended the deadline for that bounty. So you'd be submitting your audit reports and the bounty around the same time by the end of February. Uh, do have a look at the feedback given by Enrico in the last office hours. That would be helpful. With that being said, we've got our ZK resident Nagu to give us a talk on proof of solvency. Nagu, the stage is yours.
Finality. Hello, everyone. Uh, but before I start speaking, I have a little bit of cough and cold. So somewhere during the presentation, if I sneeze or cough, apologies in advance. With
Yep,
that
no
said,
issues.
let me share the screen. Probably went here again. All right. So today, I'll be discussing my notes on a paper review, paper study about the broken proofs of solvency in the blockchain custodial wallets and exchanges by G and Chakias. Um, Before I get started, so I have the notes in this form where I kind of wrote down my notes against the PDF paper and try to link them. But printing them kind of jumbles up some notes. So I also produced all the notes in a GitHub, so which I will share with you once I finish the session. So you have all the notes for you immediately. With that said, um, this paper I think is one of the very important paper for summer code because um, some Enrico kind of covered some of these attacks very briefly in his presentation when he was talking about attacks. But today I am going to be more uh, systematically go through each of those critical vulnerabilities and talk about uh, any mitigation strategies that authors proposed and a much more systematic pedagogical review. All right. Usually I kind of approach, I have my own personal approach to reading papers, which I usually like I do something called a three pass, which is basically I quickly read paper title, abstract, and try to understand as much as possible, and also the keywords. In the second pass, I try to read a little bit more introduction, a little bit background, and chapters in the paper, and try to get a picture of what it is saying, what's the main contribution of the paper. And a third pass, I go a little bit more details and try to narrow down to what the main contribution of the paper is and what the authors are really talking about. There's a lot of details when you write a paper that not necessarily important, but you still have to include them. Sometimes those details can muddy up. But if you can get the core contribution, what the main objective, what the main contribution of the paper, then that would be a very good understanding of the paper. With that said, so I kind of briefly summarized what the paper is actually is about. This paper is mainly a paper like a what we call a survey paper or a comprehensive analysis paper. So what it does is basically it presents an in-depth analysis of various proof of solvency mechanisms in the blockchain wallets and exchanges. It kind of compares with the what's the theoretical side of it versus what actually being practically implemented, and then trying to present several critical vulnerabilities in these schemes. Along with that, it systematically highlights the practical implication side of these vulnerabilities, how they might affect in real world applications. For each of the critical vulnerability the authors explained, they also propose mitigation strategies in detail that will help enhance the security of underlying these proof of solvency mechanism. They also briefly highlight where the future research should go into addressing some of these vulnerabilities and other systematic adoption issues. So in that sense, I think this paper is a very great paper for proof of solvency mechanisms. So I believe it contributed quite a bit in this survey. And typically what I do after going through this is I kind of try to gauge all the taxonomy and notation so that, if I am familiar with the paper, then I will already know a lot of stuff. If I don't, then there is a lot of jargon that I have to learn to understand what the authors are talking about. So I kind of took an attempt at what I thought are important keywords and notations here. So the paper kind of talks about POL, which is the proof of liability scheme. Uh, it basically represents P as the prover, which is the exchange in our case. U is basically the set of users. Sometimes it also represents as a U1, U2, UN. And L is the underlying liabilities data set where the prover commits on a public bulletin board or blockchain. Um, and so some of these things I may probably have, I can just skip it because you already know. For example, typical properties required for such audits, security, privacy guarantees. Um, though the paper kind of particularly devotes their time on omnibus custodial wallets, but it sort of kind of defines the other wallets, exchanges. These schemes are also valid for. Um, with that said, the paper kind of identifies 4 critical vulnerabilities across the survey. It also kind of briefly mentions which exchange, what company, and what the details are. The first one is the summation or the vulnerable summation tree, and the second one is the short hash collision, and shared user IDs, and then the inconsistent root commitments. And for each of these vulnerability, authors also present mitigation strategies. I also kind of pulled a bunch of important keywords. It kind of helps you understand particular word sometimes used in a way. For example, the public bulletin board here is essentially a blockchain ledger in this paper. So several times author kind of quotes PBB, which meant to say a blockchain. Um, I kind of leave these notes here. We go to main contributions and the list of vulnerability scheme. But if anybody has any question, I can take one or two quick questions here. Otherwise, I'll continue.
Do we have any questions? Okay, I'll go
All
with
right,
a
I'll take your
question.
silence.
No, Nagu, I have a question.
All right, good.
Yeah, it's a question regarding the types of custodials. So can you like scroll up?
Yeah,
I think so we have like two types of custodial exchanges,
yeah.
um, which require proof of solvency. The first one being omnibus custodial, and the
Mm,
second one being segregated custodial.
mm,
So for omnibus custodial, I think it becomes very difficult to prove proof of solvency because the funds of the users are in some pool on chain, and the users cannot track their funds on chain because it's in a pool. And the ledger of how what amount of coins does the custodian owes to the user is stored in some private ledger. So what could be a possible solution to efficiently prove proof of solvency for omnibus custodial exchanges? Eh,
Uh,
Yeah.
I'm not sure if, first of all, this paper is from 2022.
Mm-hmm.
So, with the history in that, I think the most sophisticated proof of solvency scheme up to that point is probably the Camacho and DOPL,
Mm-hmm.
which is the distributed auditing. And I'm not 100% sure if the distributed auditing proof of liabilities covers the omnibus custodial wallets. I have to
Right.
check that paper and
Mm-hmm.
see if it works. But
Yeah.
I'll probably answer that question after quickly checking the DOPA paper.
Yeah. Cool, cool. Yeah, in my opinion, I think that segregated custodial exchanges are far better than omnibus custodial exchanges because you can track your addresses on chain, even though it's controlled by your custodian. So, yeah.
But practically all big crypto exchanges are more like omnibus because internally they have a private ledger because none of these wallets that they share with users,
Mm-hmm.
they are actually they're actually their internal wallet. So there is a routing mechanism that happens.
Mm-hmm.
So in that sense, the funds are actually stored separately in a private ledger internally
Mm-hmm.
for many of these exchanges. So yeah, sure it will complicate a lot of stuff. Uh,
Right,
but
right.
I
Got
think
it.
even in a solvency cases, for example, oops, there's a definition somewhere in the paper that tries to talk about actually not this paper, some other paper I'll quote where it tries to define some taxonomy on what is proof of reserve, what is proof of solvency, what is proof of liability, kind of thing. But from a customer perspective, what do you want? You want to have certain kind of trust in an exchange or an entity. Plus, in if something happens, you should be able to withdraw your funds, right? So that's essentially is a proof of solvency scheme or in practice. But many of these schemes only does the first part. The second part is completely omitted from all of the schemes, where there is no way to guarantee that customer actually will be able to withdraw their funds in some cases. There is an attack, a critical attack. So a lot of this paper, a lot of this scheme implementation, they're mainly focusing on the first part, not on the withdrawal part at all. So it's uh, definitely a interesting and complicated thing. The other thing is
Yeah,
the authors kind of also highlight how little adoption from even the exchanges are for these schemes. Yeah, it's like a very, very small set of exchanges actually do any of this, either proof of reserve or proof of assets, proof of liabilities, proof of solvency. Most of them just don't do. So
that's
the
right.
the very few who are actually doing, definitely in in a better trust ecosystem from a customer's perspective, but many others are just not there. I think something came up in the chat. Maybe see.
Yep, it's a comment by
Oh,
Sebastian.
okay.
He says that segregated custodial probably adds exponentially more overhead for the exchange. That's right, because in segregated custodial, you have a lot of funds with a lot of different accounts, and this would take up a lot of nodes in the Merkle tree, um,
Yeah.
as compared to omnibus custodial. And his comment continues that he wonders if it's improved when using any roll-ups or L2s.
I'm not sure
Hmm,
how the withdrawal will be actually improved, uh, even if it's a roll up or L2. You still have the same problem.
got it. Yeah, there are like a lot of loopholes here.
Yeah. All right, let's keep on going.
Hmm.
So the main contribution of the paper, I think, is this in-depth analysis of existing schemes and identifying these key critical vulnerabilities and proposing mitigation schemes uh, for 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 uh, for vulnerability that authors kind of describe in the paper. So, with that, we will, in the next couple of minutes, we will go we'll go a little bit deeper into each of these vulnerabilities, um, and discuss how they are discussed, how they are presented in the paper, and how you can actually set up a process to exploit, and then underlying mitigation strategies, and then we can summarize at the end. The author correctly points out that there's a huge gap between what's theoretically is being happening in papers versus what actually is happening in practice. Um, and they kind of uh, correctly point out that there is so very little adoption for any of these schemes. It's not only just proof of solvency, but practically any scheme that's trying to prove, the assets are greater than liabilities kind of thing. Um, in the actual implementation they have seen, they also notice several critical errors between the actual paper or underlying theoretical algorithm versus real implementations. Um, so the four main critical vulnerabilities the authors kind of present in this paper are, like I said, it's a vulnerable summation tree, uh, which we kind of briefly went in the second lecture from Enrico. Um, and this is an interesting thing because the authors actually found the error in the audit report of Deloitte. So Deloitte kind of did some audit for some exchanges, and they actually found this error in their audit reports. So which kind of the authors comes back to and say that practically nobody's doing correctly, even if they're doing. And the second one is the basically a short hash collision where you truncate the hash and then use that for the hash. So this has a possibility of collisions. We discussed that. And then the third one is the shared user ID. So when they are building the Merkle tree, basically if you are using a user ID as a main identifier, some of the exchanges they have non-unique identifiers on their side, which resulted into errors where two users going into the same leaf node, basically. And then the last one is the inconsistent or multiple root commitments where exchanges publish different data in different places. It's going to the very first one. So the vulnerable summation tree. Let me see the picture here. Probably it's kind of a little bit helps. So in the summation tree, this is basically the very first proposal for Maxwell, and then mm, Maxwell and the very first paper Maxwell and Todd had this, and then they saw this error, and then they published a Maxwell plus paper basically. So where you have in the parent node the summation of the values from the left and right child. Uh, that's how the hash is stored. So the basic attack here is you could manipulate exchange basically can easily manipulate and reduce their liabilities by instead of putting the sum they could have basically a, a max of uh, the left and right values. So thereby they reducing their total liabilities. Here I can try to give an example where if you have a left node has let's say a 5 ETH and right node has 0, and then in this manipulated exploitation, exchange can basically pick the maximum value between 5 and 0, and then they basically contribute that to the parent's value for hashing, thereby reducing the total liabilities actually. So here the authors kind of propose a mitigation strategy by redefining the tree, and in this redefinition they basically include the values from the left and right in the parent node as is instead of the summation. So this will successfully eliminate the summation attack that we have seen in the above. There's a nice pair. Let me show you over this here. Can you see the image here, or do I need to max out?
Yep, we see the
Okay, great.
image.
Yeah.
But
So this is the original tree. Basically, you could have, so the parent is basically the summation of this 4 plus 8 is 12. So the exploit can be basically you can have where um, parent is picking the max value of 4 and 8, which results into 8, and the exchange basically submits this version of the tree to the blockchain, public blockchain. All right, let's go back to short hash. All right, so this is another exploit, another vulnerability that they saw in a bunch of exchanges where they have used a 64-bit truncated SHA-256 hash um, for all the nodes in the tree. And they kind of correctly identified that this basically leads to collisions in a very quick way. I think there is, yeah. So basically, they kind of estimate approximately what would happen in an exchange with 16 plus million users, and they estimate the hash to be about 2 to the power of 40, which is very, I mean, it's a small number in these days to attack them. So in that sense, they basically um, recommend not to use any kind of truncated hashing at all. And again, you people, exchanges can use a similar truncated uh, hash to reduce their liabilities by doing this. So in their mitigation strategy, the authors kind of propose never use a truncated hash in any of the proof of liability schemes. So the other kind of hack is basically, which was also common apparently, which is reusing the same user ID when you're building the tree. So it's a shared user ID problem. And here, same thing, the exchange has non-unique uh, user IDs when they are building the tree, and these are a number of such, BitMEX, Kraken, CoinFloor. Uh, so when you're actually building a tree, if you have the same user ID, they would go under the same leaf node, which results into basically reduced liabilities. Our exchange can also actually use this to hide liabilities. So the mitigation strategy here is again, I mean, it's obvious. Make sure that the user ID is unique when you're actually building the tree. Uh, and they also have a little bit to say in regard to GDPR compliance, because having a unique ID that identifies a user falls within this global data privacy laws. Yeah, so they kind of hello, hello, can you
yep,
hear me?
yep. Go on.
Hello.
Yeah, Nagu, we can hear you.
Okay, sorry. Yeah,
Yep.
that I lost connection. So in this sense, basically they kind of claim that when you are generating this unique ID, don't try to include any sort of PI info in it, which is basically a email address related info or phone numbers, things like the Maxwell plus plus and the distributed auditing proof of liability scheme, they both of them kind of implement a strategy like this, where when you're actually building the tree, it actually checks for the uniqueness of user ID. Um, so while I was thinking, I'm not sure if Sama, I haven't seen any code part where sort of checking for unique IDs or even writing a small unit test to see if you supply two duplicate IDs, what exactly happens in Sama's case. That could be a pretty good experiment to do. Have you ever, does anybody else, oh, I'll probably talk about this later, sorry. Maybe I'll stop here for a minute and then see if anybody has any questions.
We've got one by QPZM. Um, I'll read the question. So it
All right.
says, how can H2 equals the hash of 5 Bob audit ID B in figure 3? Can you maybe move up to figure 3, Nagu? And H2 equals the hash of 10 Bob audit ID B in the figure is the same. Does the attacker have to find a hash collision?
Well, attacker is not finding the collision. Exchange is basically hiding the liabilities here by replacing this the left value, right value with the maximum right value, choosing this.
I mean, the H2 in the figure 2 and H2 in the figure 3, is it the same or is it different?
The H in figure 3 and H in where?
Yeah, the second one, the second node in the leaf, H, it says H2, and
This is
are
H2.
they, yeah, and the one in the figure 2.
Oh, these are separate trees. The figure 2, figure 3 are separate trees.
Yeah, so the H2 in figure 2 and H2 in figure 3, they are different.
Correct, correct. Yeah, they're completely separate tree. These figures are just for showing how so for example in figure 2 it's trying to show how the Maxwell attack happens, the vulnerable summation tree, where because the parent node is taking the sum of 5 and 10 here and hashing that, and how an exchange basically can replace the sum with the max value and then basically use that as a reduced liabilities. And then they show here how exchange can basically hide certain liabilities from users if they can, under this scheme. But these two are
And,
separate trees. They're not same values.
and the client should verify the Merkle proof. And in the figure 3, does the client verify through the logic of figure 2 or figure 1?
An individual client will verify their balance, correct? So, for example, the the individual client is not trying to verify the summation hash here in the parent. They would verify their balance here, given the root and then the path.
So would you explain how can H2 in the figure 3 be calculated?
H2 here, this.
Yeah, yeah. What is the equation of
This
H2?
is just hash of the leaf node.
But the prover should uh, calculate H2 to give to the client.
It's calculated the same way as the H1, which whatever the underlying hashing algorithm they're using it, they probably have the user ID and um, the user ID and the balance, and then the hash tag, right? It's the same way how here Alice H1 is calculated, H2 will be calculated because they both are leaf nodes. Only in the parent node, right? The parent node, the summation 5 plus 5, 10 is hashed here, correct? And you can see in the hash 10 and the left node and the right node. Is that clear?
Yeah, I understand.
Oh, where we are? We are at the multiple root commitments. So this is also a very common critical vulnerability where exchanges basically publish inconsistent root commitments. So when the clients, customers are checking, they are still be able to check their individual thing, but it's actually completely wrong. And others found CoinFloor, BitMEX both had serious issues in publishing the root nodes. So this is a borderline fraud. But so obvious mitigation strategies to make sure your commitment is correct, especially commitment that's published on a public blockchain, public bulletin board, because whatever value you're committing, you cannot change it because the ledger is mutable. So those are the 4 critical vulnerabilities the author kind of talk about in this paper across multiple exchanges. Um, and then they kind of list 2 more, more systematic vulnerability or concerns in existing proof of liability schemes. One of such is basically the privacy concerns in all of these liabilities in these schemes. So they observed that either the implementation from exchanges is leaking individual liabilities or other kind of information or their balances sometimes, or total number of users, other private info in their findings. And a lot of these schemes also completely exposes the total user count of a particular exchange. So others found these issues with a lot of exchanges in their implementation, basically. they propose a number of commitments regarding various kind of stuff. They don't go into a lot of detail how exactly it's done. But for example, to hide the individual balances, liabilities, they want to use a cryptographic commitment polynomial, like a pedestrian commitment to hide that. The other two schemes that I said, the DA, the distributed auditing proof of liability scheme, kind of uses this, and the Camacho is also uses pedestrian commitments. They also propose another strategy called sparse Merkle trees, which basically, instead of using the individual balance directly, they split and shuffle the underlying liability value into multiple nodes. Um, and this is what the Maxwell implementation is about. And I think the DAPO, the distributed auditing proof of liability plus, also has SMT implementation, the sparse market implementation. But authors also say the sparse implementation is actually, I mean, from efficiency wise, is quite bad compared to the regular Merkle trees, because it actually increases the number of entries, the depth of the tree. So that's the general concern for privacy. And the last item in the paper is the dispute resolution. And this is out of the scope for SAMA, but authors kind of briefly mention that the dispute resolution is basically a open research problem. None of the existing schemes actually kind of implement it in any way for now. And these disputes can be anything, which it could be some users' balances reported correctly in the tree, or the users, their accounts don't exist in the tree. So there, for any such claims. The last concern is the private verification pattern, which basically means when a client and a user is verifying their balances, exchanges, the prover can learn which kind of users are learning, are verifying it. And then systematically in the next round of producing the proof of liability scheme, they could exclude users with a high probability who's going to verify their balances, and thus by reducing their liabilities. So they kind of propose a couple of situations for such kind of malicious poor behavior, um, which is basically outsource the verification to a trusted third party. I think Kraken is doing that right now. They also propose more research into hiding these verification patterns, how these trusted third parties also cannot learn anything in this sense. But that's about it. So I will conclude and then probably open up for more questions and the details, and I'll share the link with you. So in conclusion, the paper is a pretty good survey paper in identifying some of the critical vulnerabilities in proof of liability schemes, proof of solvency schemes. They have interacted with a lot of exchanges, and studied their implementation versus the theoretical side of the algorithms, and found many gaps between theory and practice. They are appalled by the adoption of any of these schemes by exchanges. They see they also identified user education as one key point that many of these exchanges or schemes kind of ignore, but they correctly identify that it's a very, very important aspect of proof of solvency scheme to educate the users on what they are verifying and how the process works. In general, just increasing the overall awareness and understanding of the schemes. And just like any other paper, they end with proposing more research into many of these schemes and in general, trying to produce a standard for cryptographic auditability of exchanges in cryptocurrency. Uh, so with that, I stop here and I'll take any questions you have.
Awesome. We've got 3 questions. The first one is from Sebastian. I'll read the question. Does this paper talk a lot about other proof of solvency systems, or is it more about a generalized set of vulnerabilities? If so, how do you think Summa stands out? Is it better or is it worse?
Uh, I mean, if you look at the timing wise, summer started last year, let's say. Maybe the implementation happened over the fourth quarter, something like that. But one of the original, what do I say, pseudocode or algorithm on how to do summer was proposed, I think sometime around Q2, I think, if I remember right. Paper was published in 2022, so summer is not a part of it. And summer is also um, how do I say, it's a little bit different kind of protocol in terms of especially the version 1 that we are seeing, um, or version 2 that we're going to be seeing, where we're going to use the KGG commit schemes to produce the proofs. So Summa is a little bit different protocol in that sense from the paper. The paper, but it's the same. It's a summation tree in general, but it's a broken summation tree. Summa kind of already addresses um, the all the critical vulnerabilities that are identified in the paper by the authors. The summation vulnerability, uh, uh, the short ID thing, the hash, truncated hash thing, multiple root commitments. So I think Summer kind of already fixes everything that's talking in the paper, specifically about those particular vulnerabilities. Summer doesn't touch about dispute resolution. Summer doesn't touch about any sort of verification patterns or things like this. Um, there's also, we learned about friend attack, which is basically some sort of collusion, let's say, which also is doesn't it's a very difficult problem to solve in that sense, a friend collusion, but uh, that's probably not part of the Summa too.
Great. I think this, to add some more stuff, this paper talks about the Maxwell Todd Merkle sum tree stuff
Yeah.
and not about the other proof of solvency systems such as provisions, which use homomorphic commitment schemes. So yeah, it's more about the Merkle sum tree stuff. And
Mm.
regarding the friend attack, I think difficult problems require difficult solutions. And some of the solutions I think of is, what if all the exchanges get uh, reviewed or submit their proof of solvency at the same time? Or what if we start tagging addresses, such as tagging the addresses of the exchanges on chain, and like separating them from the other whales? So, or ask the exchanges to use the same set of addresses every time. So this way, I think there would be less chances of collusion with other whales or other exchanges. But yeah, all these stuff, it's pretty complicated to implement. Mhm. Yeah,
I mean,
moving on.
reusing addresses definitely builds the trust
Yeah,
from a client and customer perspective. It sort of brands the exchange addresses. Um, but it also probably exposes them um, to losing a lot of private information. If same
that is
set of
right as well.
addresses are used, then you should be able to tell a lot about what's happening on the exchange.
That is right. Maybe we can have some sort of an anonymity set where where they do prove that they hold. Oh, we already have those, right?
Yeah.
Yeah. So, yeah, unless they expose their addresses explicitly to the people, um, yeah, using the same set of addresses is great. There should be some sort of anonymity set where they have all the addresses they own, and they prove to us every time that they own the same set of addresses and haven't colluded with any other exchanges or any other whales. Uh, yeah, that would work.
I mean, this is
It's
actually
really,
I think a mitigation strategy if there is a collusion between two exchanges, let's say.
mm-hmm,
Let's say both exchanges have same set of users and you're using the same funds
mm-hmm.
and they are essentially exchanging I don't know, their proof or signatures or whatever it is. How do you prove, right? So both of them technically can do a reduced liabilities because they are using the same funds from, let's say, certain
Hmm.
users.
Yeah, it's a tough problem to tackle. Maybe they all could get audited at the same time, or we can come up with really clever solutions to this where they all sign some message to prove that they are not colluding. Yeah, but it's an extremely difficult problem to tackle. Yeah.
So let's go to next question.
hmm Yash says that he had a concern regarding SMT, where the exchange can troll its users to reduce their credibility when they report. The exchange can send proof of all leaves, but one to the user, who then tells everyone that the exchange didn't tally correctly. The exchange now comes and publicly announces all the users' leaves to prove themselves, thereby also revealing user data who challenged the exchange. Hmm, that's like a complicated solution and a complicated question. Nagu, what do you have to say to this?
I mean, I don't know about this scenario, but I can see the other scenario. Let's say there's a very big whale in the exchange. Let's say he or she owns 50% of the funds, right?
Mm-hmm.
So exchange can technically collude with this one single user, right? And exchange can do everything right, right? But what exchange does offline is goes to the user, this whale, and tells you, hey, no, if there is any kind of critical vulnerability shows up, then you will be the first one to get paid, and we have funds, right?
Mm-hmm.
And then that whale verifies the exchange has funds, and then sets up, and then he gets a priority to get reimbursed. So what happens in the remaining all users, they correctly verify their proofs, but exchange only has 50% funds actually. So they are reporting 50% less liabilities, and everything can just go as is. So you can have uh, uh, such a such a scenario also where just one very big user or a few very big accounts can collude with the exchange, whereas you could still have 99.99% users correctly verifying their proofs, but still the whole system could be uh, not solvent.
Right. I think Yash's question was more about how does a user prove that the user's balance hasn't been reported correctly? What would happen in case of that? There isn't any
In
scenario where the exchange would come and publicly announce all the users' balance to prove themselves. That's unlikely to happen. But how does a user prove that they were misaccounted or their balance was not included well? Is that
uh,
even an open research problem?
Yeah, this second order effect is actually not covered by any of the schemes.
Mm-hmm.
So they can only prove, okay, my balance is wrong. But the meta question, hey, here, how can I prove my balance is wrong, is not provable in any of these schemes. So this is where dispute resolution need to kick in to say, okay, otherwise you probably need another zero knowledge proof that I have correctly verified my verified balance.
Mm-hmm.
Right.
You probably need a zero knowledge proof to prove that the zero knowledge proof provided by the custodian that your user, the balance used by you, has been included
Right.
in the Merkle sum tree is incorrect. That's
So
really complicated. Yeah.
yeah, so his user has there should be another process that says, okay, this particular user has proved that they correctly verified their balance. Otherwise, there is nothing in the system that can actually say that they have correctly proved or verified.
Got it. The final question we have from QPZM is it's regarding figure 2 and figure 3. The question is the root node in figure 2 and figure 3 the same? If they are different, the Merkle proof of H1 will fail. Uh, I thought they will be different because V2 is 10 in figure 2 and V2 is 5 in
Max
figure
does.
3.
Yeah, they're different. They're separate trees.
So the root node in both the figures are different.
Yeah.
Mm-hmm.
So after reading
QPCM.
the paper, I thought maybe the non-unique ID is a pretty good first test for Sama. There must be a way to, without having a huge machine to check, to create a CSV file with duplicate IDs and see how Sama actually addresses this issue. I mean, that's something that we can practically, I mean, take something practically away from this paper review. There's otherwise the other critical vulnerabilities are addressed by Sama.
Mm-mm. Awesome. Do we have any more questions? All right, I'll take your silence as a no. And yeah, Nagu, I think we have one last question from Sebastian. So the question is, I think Suma is not concerned with the user ID and is delegating that task to the custodian. At least obscuring the user ID by hashing is suggested to prevent brute force. Yeah, that's right. I think we cannot do anything about the user ID in the circuit level. There can be tools outside the circuit. Uh, yeah, this falls on the part of the custodian. What do you say, Nagu?
I think, but it's only selecting, it's it's an optimistic situation where Sama's protocol is assuming poor is avoiding such some malicious behavior, right? So, for example, the circuit should be able to address if there's a duplicate ID. Otherwise, the IDs would basically go on the same leaf node, right? So, for example, a prover who is honest but let's say malicious, he wants to reduce his liabilities. They use Sama's code and they let's say hide a bunch of liabilities by duplicating user IDs and thereby reducing the total liabilities. Uh, let's say after some time, somebody finds out where should be the mistake be. The mistake should be in the protocol implementation that it's not addressed. So the mistake should be on the sideline where, hey, this is a bad behavior, it's not covered by the protocol. I believe it should be part of the protocol. If you when you're reading the CSV file, it should be able to check if duplicate IDs are passed.
Awesome. Any more questions? All right, so let's wrap up. I think it was an awesome presentation, Nagu, and the fellows can continue to learn about proof of solvency and feel free to ask questions in the Soma General channel. Just to remind you all, we have the deadlines for the bounty as well as the audit reports coming up. So yeah, go ahead with your teams and find those bugs. Thank you, everyone. See you in the
Thank
next
you.
session. Bye bye.
All right, bye bye.